Okay, stop it.
Ja, alles klar.
Where is the...
Ja, baš avtomatski.
Waiting for the secretary. The secretary is the key for the...
Glavna tajnica ima ključ od tega, pa je na malci.
And people in the...
Elena is not here. Yeah, she's... Oh. Okay.
Good morning, everybody in the stream. Can you hear me? Can people hear me in the stream? If somebody puts their thumb up or...
Yes, we can hear you.
Ah, lovely. Thank you.
Okay. Torej, lepo pozdravljeni pri drugem delu našega seminarja o rabi umetne inteligence v humanistiki. Lepo pozdravljeni. So we will welcome to the second part of our workshop on AI applications in humanities. Because we are running late already, we will, without further ado, I will let the floor to you, Josef.
Yeah, no, thank you very much again, and welcome. Many people are back. We also have a couple of new people, and I would like to start with a quick recap of what we did yesterday, and then we launch into the final part of the seminar. Okay, so this is the exam part. So what's an artificial neural network? No, let me start different. What's an artificial neural? How does it work? What is it as an abstract level? In your own words, how would you describe it, given what you heard yesterday? An artificial neuron. There is some? Yeah. So we have some input. Okay. And how many inputs can we have? Yeah. Any number. It could be 4, it could be 400, 4,000. Yeah. In artificial neural networks, in artificial neurons, I should say. What are these inputs? Yeah, just numbers. Okay, and if I have 4,000 inputs to the neuron, the vector, whatever size, the dimensionality of 4,000, and then 4,000 numbers in there. Okay, so that's the inputs. Okay. And then as the next step, what happens with those inputs? Each one of them. Yes. Yeah, very good. So each of these inputs, it's like a wire, signals coming in, the signals coming in, another wire, maybe 4,000. And on each wire, we have sort of a resistance, a weight. And what is done with that weight and that input?
What level that taking?
Oh, very good. Okay. And it's done by multiplying the input with that weight. Yeah, remember the weight is 1, the input is going to sort of go through to the central part of the artificial neuron. If the weight is 0.5, then only 0.5 of the input strength is going to end up with the neuron. If it's 0.1, then only 1/10 of the input strength. If it's negative, then it's going to flip the value of the input. So it can be positive and negative. Okay. So we have these weighted inputs. We just get each input, we multiply it with its weight. Then what do we do? What do we do with these 4 weighted inputs or 4,000 weighted inputs? In the artificial neuron, in analogy to the biological neuron. Yeah, we sum them, very good. Okay. And that term is called the sum of the weighted inputs. Okay. All right. So we have got all the inputs. Each one is weighted by a particular weight, whatever that happens to be at that time. Okay. Then we sum over all of these weighted inputs. And then what's the final thing that's going to happen in the artificial neuron?
The final station of.
Yeah, it's going to fire. Okay. And there's sort of like a transmission function, an activation function, a threshold. Yeah. And we use sigmoid, and that's a nonlinearity. It's a nonlinear function. And it models that biological aspect of biological neurons, where we said that, biological neurons, they get information in the form of charges, electricity, and all these charges are summed at the core of the cell. And if there's enough of a charge, say enough information, then that biological neuron will fire. Okay, and the artificial neuron kind of like, models. Yeah, very good. So everybody pass that part, please. So this is an artificial neuron. Okay. What is an artificial neural network? Yeah, so lots of these fellas. Yeah. And in our brains, we have like, 500 to 1,000 billion estimated kind of, biological neurons. Each one is connected to roughly 10,000 other neurons. Okay, so it's like, 500,000 billion or 1,000 billion times 10,000 or something like that. That's all the connection. And can anybody in their own words, from what we said last time, explain a little bit what's the metaphor? How does learning happen? First of all, what are the things that do the learning? What are the parameters in such artificial neural networks? And how does learning happen?
Arabic learning.
Yeah. Okay.
The connection.
And the connections, and the weights.
Yeah, in the way.
Very good. And yeah, it's error-based learning. So
Back.
propagation. Yeah. Very good. Yeah. Okay. So kind of, that's sort of like the metaphor, the biological metaphor. But these neurons are all cross-connected. And if we learn something new, then we sort of like make the connections between some neurons that are responsible for whatever it is new that we're learning. Like, I don't know. I think we talk about salsa dancing, inline blading, whatever it is, or learning a new language, or I don't know, vector calculus or something like that. You just make those connections stronger. Forgetting is kind of like corresponding to weakening the connections, like, lowering the weights, making the weights smaller so that the information, is sort of like squeezed, but you get through that well. You can remember that? Yeah. And then the whole thing kind of like initially from artificial neural network. How do we get the weight? Random. Yeah, we just take it. Oh, very good.
Thank you very much. So we take a random number generator, we run it over the network, we randomly initialize all the weights, and then we use data to train this neural network, this artificial neural network. And we looked at this doggy and cat example. How did that work? What needed to be special about the data? Yeah, it had to be labeled. Okay, so we had 100,000 pictures, like, cats and dogs, and each one of them had to have the correct label. Like, this is a doggy, that's a cat, that's a cat, that's a cat, this is a doggy. Okay, and then we feed that first picture into the neural network. What like, under the hood, how is that picture represented? If it's like, it's a digital camera. Yeah, it's a vector. It's a vector of numbers. It's just numbers. So photos, kind of like on your smartphones, are just numbers, just a vector of numbers. And that's what neural networks can process. So that it takes in that vector. Initially, all the weights are randomly initialized, and you do the forward propagation. For each of the neuron in the next layer, you calculate the sum of the weighted inputs. For each one of them, you send it through the nonlinear activation function. And that actually defines then the output of that local neuron and all the other ones in that particular layer. And the output of the neurons at that layer are then the input to the neurons at the next layer, and so on, until I get to the output neurons. All right. And then, of course, kind of like initially, the neural network is not trained. All the weights are completely random. So I feed in a picture of this little puppy doggy, and most likely the network is going to say what? It's not. Yeah, it's a cat. It's not going to get it right because all the weights are assigned randomly. But I know that this should be a doggy. Okay. So from that information, I can calculate an error. Yeah. No, from the data. Yeah. Yeah, exactly. Yeah, we program the network in such a way that it knows for that particular data item what should be the correct label. We just take that from the training data because the training data is labeled. Okay, and so we know that these two output neurons, where the first one, let's say, is for the dogs, the second one is for cats. That if it's a doggy picture, the output neuron for dogs, should have high excitation or I don't know what was the other word that we use? Activation. And the one for cats should have lower activation. And of course, initially, that's probably not the case. Get some crazy results. And I compute an error. I compute an error between the output of the network and what it should have outputted. And I take that error, and what do I do with that error then? I square it often. Why do I do that? Yeah, very good. Yeah, yeah. Because if I just took the difference, very good. Excellent. But just took the difference. Some of the positive errors would cancel the negative errors, and we don't want that, so we just square all of these fellas, and that takes away all the negativity, and it also gives us a nice shape for the loss function. We saw that for a single parameter, the loss function, because it's squared. Remember, it's a parabola. Okay, and then for every value of that weight, I know where I'm on the parabola. So if the weight happens to have this value, I take the partial derivative of that parabola, and that for example might say, okay, it's positive and it's fairly steep, and that means I have to lower the weight, and I can increase it by quite a bit. I can decrease it by quite a bit. Yeah, so it's the size and the direction of the error that I use to update the weights, and I do this layer by layer by layer when I go back in this neural network, and that's called backpropagation. Okay, backpropagation for those of you who have a computer science background is actually a version of a dynamic programming algorithm. It's just a clever way of doing things without too much effort. And what you trade is storing information rather than recomputing it, essentially. And if we didn't have this, we couldn't train the big networks. No chance. Complexity is too much. Yeah. And then we do this for the whole 100,000 pictures. And then the weights are after some time, we might go over the 100,000 again and again and again. We might do this 3 times, 4 times, maybe only once. And we can track the error. We can see how the average error is developing, and if it's good enough, if it's sort of bottoming out. Initially the error is very high, and then overtraining it gets lower and lower and lower, and then it's sort of I don't know, pretty stable, and then we stop training usually, because nothing much is happening anymore. Okay, and then we can give new pictures to the network that is never seen, and hopefully the network has generalized over what it saw in training, and is still I don't know, if in training it got 90% of the examples wrong, and for unseen data it gets 85% of the 90% of the examples right, and if for unseen data it gets 85% of the example right, that's very good. But these image recognition neural networks, they can be super good now. So 99.999 whatever, kind of they're kind of superhuman. In some respects. I mentioned the example of the radiologist. Kind of neural network are much better at spotting cancer than the best humans, for example. Of course, they still work in tandem. There's always a human doctor, and he or she will validate what the network did. But if you have trouble with that, ask for an AI to look at your X-ray as well. It doesn't do any harm. Okay, so that's a neural network. Okay, and then we talked about language models. And this is all part of kind of getting a good idea about the ingredients that make up large language models. So we've got the neural networks, and then sort of language models. And initially we talked about count-based discrete language models. Yeah. So what do they do? What does a language model do? What did these fellows do? Yeah. A language model, in general, what do they do? Yeah. Yeah. What kind of thing do they predict given a context? Language patterns, yeah, yeah. Yeah, likely next words. Do you remember that? Yeah, we did once upon a time, and then we had lots and lots of other examples. And you were able to guess likely continuations, step by step by step. And that shows kind of that we as humans, we also have a language model as part of our intelligence language faculty in our heads. We can do this even in other languages, because we did this in English. Yeah, and you pretty much agreed on the unlikely next words and on the unlikely ones and stuff like that. So basically what a language model does is, given a context, and the context is just kind of like, prefix, like, a couple of words that have been said, like, and it tries to guess what are likely continuations, word by word by word. It will give you likely next word, we'll push that into the context, then you have a new context that has been extended by the next word, predict the next word, etc. Okay, and formally, that happens in terms of the language model somehow trying to compute a probability distribution over all possible words in the language, given a particular prefix. Do you remember that? And that we modeled that with conditional probabilities. And for discrete count-based language models, we did this with just counting. Kind of like, do you remember the formula for like conditional probabilities? Yeah. So we just estimate them from large data. Okay? And that works pretty well. We saw the Shakespeare example. But there was a big problem with it. What was the big problem with it? Yeah, the zeros, exactly. Very good. So if you want to condition on long context, and we really want to do that, kind of like, because the better we can condition on long context, the better is our model. Do you remember, like, the bigram model doesn't see some of the mistakes, and a trigram model already sees the mistakes, but theoretically, some of these long distance dependencies in languages, that can be, miles. Do you remember that example? I used to live in France. I still try to go every blah, blah, blah. I love the cuisine and I like the wines even better. I still have many friends there. Unfortunately, I still don't speak good. Oh, yeah. And the mention of France was like 3 pages ago. Okay, so theoretically, there can be, long distance dependencies can be very, very long. Okay, but we had to do that Markov restriction, the bigrams, the trigrams, the fourgrams, because like, the longer the history that we want to model, and we really want to model that, kind of like, the less likely it is to ever see to have this attested in the data, even if we have like half the internet or something like that. And it's simply because the space of possible variations is too big. Okay, all right. And then we saw how, so that was the discrete count-based language models. And then we saw, how neural networks can come to the rescue. And for that, we looked at a different neural network architecture. Up to that stage yesterday, we'd only looked at feed-forward neural networks, okay, which are fixed input, fixed output. Because I have so many input neurons, it might be 4,000 or I don't know, 40,000 or 400,000 or 4, something like this, and I have fixed output, okay. But for language models and for many language applications, language technology applications, we'd really like something that is flexible, that can sort of like adapt itself to any length input and generate any length output. Okay, remember these models were called sequence-to-sequence models. I didn't actually mention that word, so that's an important word: sequence-to-sequence, sec-to-sec, and that means you have a neural network that can take any arbitrary input length sequence, and from it generate any arbitrary length output sequence. And the length of the input does not need to be the same as the length of the output. And you all know this from translation. Like sometimes the input sentence is longer, sometimes the output sentence is longer. It does not need, like, I don't know, a 5-sentence input in English may generate, like, I don't know, 5-word sentence in English may generate like a 7-word sentence in German, and vice versa. Yeah. So what was the kind of neural network that we used for, that has these properties, that can it unroll itself to any input sequence very elegantly? Recurrent neural networks, the RNNs. Yeah, very good. Okay, and you kind of like roughly remember, I guess, how they work, and how you can make encoder-decoder systems that take arbitrary length input and can generate arbitrary length output and stuff like that. And we also saw an example where we can use this as a language model. Okay, it would just be an encoder, and it would be trained in its output at each step to predict the next word. Okay, now, and this is again fundamental. Why does this overcome that limitation that we found in count-based discrete language models, where we have to, in order to estimate the probabilities, do all this counting? What was the big difference? Why can these RNNs in principle, yeah, very good. Okay, so in the count-based models, if we use count-based estimations of probabilities, okay, for a given context, we have to have seen that context in our data, and ideally a couple of times, because otherwise, if we see something only once, probabilities are not very reliable. Kind of like, But the longer the history that we want to model in the count-based models, the less likely it is that we ever see this in the data, okay? And now the neural network-based language models, they do this differently. The only thing I need is kind of like, for each word in the input, I need a word embedding. Yeah, so I have to have seen the word somehow, but not necessarily in that context, okay? And then, you know, the recurrent neural network just computes a hidden representation, which is a neural representation of all the context, okay? And then just integrates that with the word embedding of the next word, whatever it is, and computes a new context. Yeah, you saw the little neural network that does that, and that was no different from the other ones that you've seen. Yeah, you see that that's the reason. Yeah, and we also, I think we briefly talked about subword encodings. You know that these neural networks, they don't actually compute with words, with linguistic words. They kind of like, they chop them up in clever ways, statistically, but just kind of like, you know, counting letters and merging letters and stuff like that. It's a trick from compact encoding. But there are various versions of that. You know, some companies do something that's called byte pair encoding. Other companies or other researchers do what is it? Sentence pieces is called, or word pieces. And you know, like if you're Microsoft, you do one. If you're Google, you do one. If you're like, you know, but they're all very similar. So under the hood, they compute with these fragments, and only like in the input and the output, they show us kind of like words. But you know, inside they're not words. Yeah. So some of them are words, yeah, some of them. Okay, so that's great. So we now have neural language models. What was the problem? And that's roughly where we ended last time. What was the problem with these RNNs? Yeah, okay. So these recurrent neural networks, even though they theoretically allow us to do like, you know, sequences of infinite length and sequence-to-sequence models and all of that, they actually get a little bit hazy in their heads, like, you know, for input that is a long way away. So, like, you know, an old style RNN, you know, beyond the history of 10, 12 words or something like that, depending on so many things, how many training data you have, how many neurons you have, like in these fellas, they get a little bit hazy. Kind of like, you know, so the old style machine translation, for example, was very good. Neural machine translation was very good on pretty short sentences, up to like, I don't know, 15, 20 words or something like this. But then after that, for long sentences, statistical machine translation was much, much better about 10 years ago. And the reason is that bottleneck, kind of like, you know, the bottleneck in the encoder, or the ability of these RNNs to actually really only model limited context. And because it's too far away, they forget things. It's similar to us. Kind of like, you know, and the attention was a way to overcome that. Yeah. And do you remember what happens with attention? Kind of like, could you describe this? Let me just go back to this. Oh, you have to click that fella. No, so I'm talking so much, this fella's falling asleep. So that was the attention thingy, kind of like, you know, can you say in your own word what this kind of like did? It's a sequence-to-sequence model. So we've got the encoder here. That's the A's down there. That's our input string. Let's say we want to translate. The B fellas are the output in a machine translation example. What does the attention do? And without attention, we had this bottleneck here. Remember that? Yeah, because we have to squeeze anything through that vector. And even if he's 512 or 1024 or 2048 or 4096 or something like that, you know, it has its limitations. Okay. Oh, he's turning nicely. How does that guy here overcome? Yeah, that's essentially it. Okay. So here in the output, it's generating output words step by step by step based on the input, on the hidden representation of the input. Okay. So this output hidden representation, that one over there, that arrow, okay, that's a vector, it's a hidden state. And that summarizes what the decoder has generated already, kind of like here the first word, and everything that's supposed to be translated. Yeah, it's a hidden representation. Okay, it's just an RNN that is not, you know, reading in new words, but it's generating. It's just generating. You know, in its history, it's just recording what it is generated. Okay. All right, and what it does is it takes that instruction of what to do next, kind of like, you know, because that encodes kind of like what still needs to be done in some sense, you know, and it takes that back and compares that hidden state, that vector, with all the hidden states of the encoder. Okay, and the comparison is just a multiplication over here, over there, over there, over there. So you get a number here, there, there, there. And the bigger the number, the more similar the hidden representation here is to the next step, to the current instruction, for the decoder. And then I take these numbers, I make probabilities out of them, and then according to these probabilities, I take each of these hidden states of the encoder, I multiply each one by its respective probability, kind of like, how important is it? How similar is it to the next task? And then I use these weighted representations and sum them and give them as an additional input for generation of the next fella here in the decoder. And I do this step by step by step. So every time, once I move on, once I've generated this one here, I move on there, I feed that back, compare it to the input. And you can see that what I do here is I dynamically recompute what is important in the input for the next step of the translation. Okay, so there's no kind of like one fixed bottleneck, representation that is sort of like, that has to do all the work once and for all. Yeah, everybody got that? Okay, very good. So final thing before we cover the new stuff, there's another big problem with these RNNs. Better versions of RNNs, they're LSTMs and stuff like that. They can remember 100 words or so. That's all fine, but there's a problem with them. What was the other problem with them? Do you remember I said they're inherently, what word did I use? Inherently sequential, very good. They're inherently sequential, and they're also inherently sequential in training. Because after each step, kind of like, you have to look at the output, compute some error, and then go back all the way to where this fella started. Because, any step in between, the current new input or current new output, doesn't matter, kind of like, is potentially also responsible for the error to some extent. Yeah, so every step I have to do this back propagation in time, compute error, backprop, compute error, backprop, compute error, backprop. And the longer these sequences are, kind of like, the higher the risk of like, fading gradients, exploding gradients and stuff like that. And more importantly, you can't really parallelize this, at least not theoretically, mathematically. I mean, like, you may have noticed that about 10 years ago, your smartphones were doing perfect dictation. You didn't have to train them anymore and stuff like that. So speech recognition on your smartphones, around 10 years ago, a bit longer actually. And that was done with RNNs, LSTMs, with these guys. And of course, for Google initially, on Android, they had to scale this to 500 million or 1 billion Android phones. So they had to find a way to make this as parallel as possible. Kind of like, but that's super hard engineering work, and it's approximations. So they had to do something like this. But theoretically, like, you can't really, like, because you have to compute everything beforehand before you get some new input, and then again. So it's inherently sequential. Yeah. Okay. Okay. Now we're coming to the new stuff. Okay, and the new stuff is the transformer architecture. I think we covered all of this. And the transformer architecture is another type of neural network. And I mentioned this last time. It's one of the highest cited papers ever in science and technology. So I looked this up a couple of days. So up to now, I think 2 days ago or 3 days ago, it was cited over 200,000 times. And yeah, that's just absolutely amazing. That's sort of like, I don't know, it's as many citations as some entire universities have, like with all their researchers and stuff. It's a single paper. And there's a reason for that. And the reason, so all the modern large language models are based on transformer architectures. And the reason behind it was to come up with a neural network architecture that is easily parallelizable and is as performant, maybe even sometimes a bit higher performant as LSTMs, RNNs, or something like that. Yeah. So you can also make some very, very high performance systems with LSTMs and RNNs, but as I said, kind of like, they lack this easy parallelization thing. And the transformer was really built for that. And I'm going through some of the intuitions. And that's the neural network architecture and technology that's underlying all the Geminis, the ChatGPT, and all the models that we have today. And it's this architecture that enables the companies and researchers to scale this to the data of all the internet to make the networks really, really large. Like some of the actual networks nowadays, they have thousands of billions of parameters. And yeah, and that's what this architecture enables us to do. Okay, so motivation is easily parallelizable, no recurrences in RNNs, high performance, and it's based on extensive use of attention. Okay. And the title of the paper is "Attention is All You Need." You know, that's a pun on the Beatles song, like "Love is all you need." So they kind of like, you know, said like, no, attention is all you need. And the variants of this architecture. So this is what a transformer looks like. And let me just talk you through this. Kind of like, this is at a very, very high level, just to give you the basic idea. So this one that you see here is also an encoder-decoder architecture. So that's the encoder, this fella here, and that's the decoder. Okay, so it's basically a sequence-to-sequence architecture. It was designed for machine translation. So originally the motivation for the transformer was machine translation. Okay, so encoder, decoder. So you can take arbitrary length input sequence, like in one language, and you can translate it into another language. So the encoder reads in the input that's to be translated, and the decoder produces the output, the translations. Okay? The inputs are word embeddings. Okay, so the sentence to be translated is presented to the transformer. For each word is word embeddings. You know, and we compute them. Like, you know, you saw like, you know, how we can compute them, etc. Okay. Then in the encoder, there are normally, like in the vanilla original transformer architecture, there's 5 of these encoder blocks, not 5, 6 encoder blocks. So you see the NX here, so that's supposed to mean like, you know, I don't know, n of these guys stacked on top of each other. Yeah, and it used to be 6, kind of like initially. And inside the encoder, we have the attention over here, and then a feed-forward network. Okay, like, just ignore all the other stuff. Okay, and the decoder, you know, is also, you know, a stack of blocks over here. And in the original architectures, we used to have like as many encoder blocks as we used to have decoder blocks. So if we had 6 encoder blocks, we used 6 decoder blocks. And the encoder and decoder blocks are linked here by something that is called cross-attention. Okay, and this cross-attention only has access to the top layer of these 6 blocks. You know, so we take our input sentence, we send it through the first block, the second block, third block, fourth block, fifth block, sixth block, and that at the end, kind of like, you know, we share that information with the decoder. And this attention here, that is called cross attention, is the same type of attention that you've seen before, where the decoder is supposed to generate something, and he goes back and gets some information from the thing that it's supposed to translate or something like that. Yeah. But then the decoder, just like the encoder, also has its own internal attention. Okay? And this attention over here in the encoder is called self-attention. So this one here is cross-attention from the decoder to the encoder. Like the decoder peeking into the encoder, what is it that I have to translate? Okay? The self-attention over here in the encoder and the self-attention here in the decoder, they do something else. Self-attention in the encoder takes the input sentence that I want to translate and makes 2 copies of that sentence. Okay? So I have the sentence there twice. And then it compares each word in the copy, you know, first word in the copy, with each ones in the original sentence. And it does that by just multiplying the vectors. Okay? And then it sort of like sees kind of like, you know, which words in the input sentence are similar to this word, which are important to this one. And then it computes a new representation of the input word based on the sum of all the weighted input words that are important for this word. And it does this for each input word. Okay? So up to here, you know, in the first level, when we feed in the words of the sentence to be translated into the transformer, these are word embeddings. And these are static embeddings. You know, they don't model context. But the self-attention in here takes these word embeddings and hyper-contextualizes it. Yeah, because I mean, you all know, like especially the linguists here, that, you know, words can mean many things, and it depends on context. And in the self-attention, hyper-contextualization will happen. So at each layer, I more and more contextualize the input words. You know, all of the layers do the same. This is just a feed-forward network that sort of like stores a bit of knowledge and stuff like that, if you like. Yeah. And then in the decoder, I also have self-attention. Because in the decoder, you want, you know, when the decoder has generated 5 words or something like this, and it's supposed to generate the 6th word of the translation, you want to let the decoder to be able to look back on the previous 5 words he has generated. Okay, and the decoder does that at each step, also using self-attention, where it compares kind of like, you know, all the words to the ones he's already generated. But at each stage, it's not allowed to look into the future. Kind of like, because, you know, if you allowed it to look into the future, it would just learn to copy. You know, it would, from the training data, it would just learn to copy the right translation. Yeah, and you can't do that. So at this stage here, you know, you've got mask self-attention, and for each word that you're generating, you can only look at the previous ones. Okay, and the ones that come after, which you see in training, for that particular fella, are out of bounds. You know, you put a mask over that. It's the same mechanism. You just put a mask over it. You kind of like, you know, turn him blind on one eye so he doesn't see the future. Okay, so that's the general architecture. So 6 of these blocks that take the word embeddings, the decontextualized, the static word embeddings, they hyper-contextualize them in that sentence. And I'll show you an example of that, you know, to give you better intuitions. You know, it does this in 6 levels. It does this in parallel. So all the words that are coming in, the big matrices, you know, lots of multiplications and stuff like this, all happening in parallel. There's no notion of sequentiality. You know? And as there's no notion of sequentiality, you have to associate each input token representation, which is just a word embedding, with a positional encoding. Because otherwise the transformer would not know this is the first word, second word, because there is no, it's like an RNN knows what is the first, second, because it does everything by clock. First one, second one, third one, yeah. So each hidden representation has a representation of how things went. That's absent here. You know, we're doing everything in parallel. So we have to add an input embedding, a positional encoding to the input embedding. And the positional encoding is kind of like, you know, linguists will be horrified. The way it's done is kind of, you just take the sentence and then you put sine waves and cosine waves at different frequencies over the sentence. And for each word, you just take that slice. You know, the sine is this value, the cosine is that value. So for the first word, kind of like, you know, what's the sine of 0 degrees? 0. What's the cosine? It's 1. Okay. Then for the second word, what's the sine? What's the cosine? It changes. Kind of like, no, and you do this at different frequencies, so you can do this for any length input. Okay. And these positional encodings are just embeddings. Okay. There's a sequence of numbers of these sines and cosine values for the position. And you just add them to, it's actually, you know, position-wise addition to the word embeddings. And of course, you know, this is a little bit subtle because you don't want to give it too much positional information overriding essential word embedding information, but you have to give it enough positional encoding so that the transformer knows that, you know, John loves Mary is not the same as Mary loves John. You know, the source of many a tragedy, you know, it makes a difference. Yeah. And that's how you do it with these positional encodings. So like kind of like, you know, this looks, if you're from linguistics, you think like, you know, are they totally bonkers? No, they're not. They're very smart. Okay, so, and then kind of like, so that input goes in parallel, the whole sentence. So this, like the classical transformer architecture, I think allows you 512 tokens, so power of 2. You know, these tokens are subwords, they're not words. So this corresponds to, I don't know, roughly 400 words, 450 words or something like that, depending on the subword encoding and stuff like that. So that's already, you know, a good context. Kind of like, you know, and it's hyper contextualized because the self-attention contextualizes everything in there and everything happening in parallel. So you do this like the input first block, then the second block takes the output from the first block, then the third block takes the output of the second block, and so on. So 6 blocks. Then you've got an embedding, hyper contextualized embedding for each of the input words at the top of the 6th block. And these hyper contextualized embeddings are accessible via cross attention to the decoder. The decoder is, you know, remember that originally this was done for machine translation. The decoder now has to translate. And this is where the decoder looks back at, what do I have to translate? And for each stage, kind of like, it can look back again and say, for the next word, what's important, like you've seen before, okay? And in the decoder, again, you have the same thing. So you have a self-attention head. It's called mask self-attention over here because it's not allowed to look into the future. Because in training the system, the correct output is given to the system in parallel as well. Okay? There is no notion of recurrency. It sees everything. It sees the gold output. Okay? It's called teacher forcing. And that allows you to also do learning the decoding completely in parallel. And because of that, you need this masked self-attention where for each token that you're trying to learn, you know, for the translation, you're not allowed from that token onward to look into the future. Because otherwise, if you switch the masked bit off in the self-attention over here, the thing would just learn to copy and would not learn anything. Yeah? All right. So that's kind of like, any questions about that? That's kind of like a lot to take in. But remember that the motivation was not so much to kind of like, you know, come up with a neural network architecture that is like 1,000 times better than RNNs or LSTMs. It was to come up with something that's completely parallelizable during training. You know, during prediction, once you've trained the system, when it translates, it actually goes sequential in the decoder. But during training, it's completely parallel. Okay, and it's highly performant, and it's based on some ideas that we've seen before. Sort of like self-attention, mask self-attention, and cross-attention. Okay, do you get kind of like a rough idea how this kind of like works? Okay, so let's go into a little bit of detail. So here's kind of like the slides are from a good blog about the transformer architecture. It's Jay Alamar's blog, and if you want to look it up again, it's a nice one to read. It's not very technical. But it gives you the basic idea. So here is kind of like a transformer in the abstract. And you can see it's a machine translation system. And I'm translating here from je suis étudiant to I'm a student or something like that. Yeah. So that's the encoder. That's the decoder. Here you see the encoder on the left and the decoder on the right. Yeah. So it's kind of like really high level. Now, each of these encoders and each of these decoders is a stack of 6 encoder blocks and a stack of 6 decoder blocks. See that over here? I have 6 of these fellas on the left, and I have 6 of those fellas on the right. And the cross attention is only from the top encoder block, you know, where the transformer has munched through all the input that it has to translate. Okay, and then it passes the information to the decoder, but it passes that information to the decoder in terms of cross attention to all of the decoder blocks at each level. Yeah. Okay. And sort of like a couple of years after the transformer architecture came out, people looked into what do these levels of encoders and decoders actually learn. And it turns out that, do you remember that feature and representation learning picture that I showed you, kind of like with 1,000 image classification task and stuff like that? And something like this is happening here as well. So the lower encoder blocks, they learn something about words, the neighborhoods of words, a little bit like morphology and stuff like that. The middle ones are a bit closer to syntax. The higher ones kind of like to semantics. They're not the same as our morphologies, as our semantics, as our like syntax or something like that, you know. But you can use probing experiments to show that there's information in there that is similar, you know. But the machine comes up with that, and one of the reasons, so this is feature representation, and remember, this is one of the reasons why some of these neural networks can have superhuman performance. And actually for machine translation nowadays, for languages where we have a lot of training data, neural networks are better than the best human translators. But they still need to be checked by human translators because kind of like, you know, somebody has to vouchsafe. It's not that the jobs disappear, on the contrary, but the human jobs change. Okay. And in order to then, if you're a human translator, for example, to put your stamp on a translation, or to, you know, and transformer will also make mistakes like humans, to correct the mistakes in post-editing, you need to be as well trained as a human translator as you needed 5 years ago, 10 years ago, 20 years ago, including cultural knowledge and Landeskunde and stuff like that, kind of like, you know, but your role is more supervisory. Kind of like, depends. I mean, like, you know, the big companies, like, for example, they estimate that even now, they only can translate around 5% of what they would like to translate. you know, and some translation, of course, kind of like you don't need supervised by human. Like if it's sort of like, you know, like actually, I mean, like Microsoft and some other big companies already did this 40, 50 years ago when translation was pretty awful. But I mean, they were selling across the world and they actually machine translated all their technical documentation, awful results, you know, but still, these awful translations in Spanish were helpful to the Spanish engineers when they were trying to fix a problem, like in Argentina or in Spain or something like this. So they had the original English, which of course was perfect, the technical documentation, and they had a crappy Spanish one. And with those two together, an expert could often work out, you know, even though that he or she, that engineer did not have very good English and stuff like that. So the big companies have done it like for donkeys years. There is no other way. There's too many languages. I mean, there's linguists among you know that in linguistics we estimate that there are about 7,000 languages in the world, you know, and there's no chance. Yeah? But even for the big ones, you know, there's the demand for translation in modern world is still absolutely massive. But it would change the jobs. The jobs is not the same anymore. Kind of like, you know, for some stuff, you will rather take you will take a pre-translation automatically generated translation from a neural network and then post-edit it. And if it's okay, so you find some mistakes, you change them, and then you put a stamp there. It's more like a notary, you know, or like, you know, in a big translation company where you have, for a big project in a big translation company, you might have 50, 100 human translators working on the documents at the same time. And then you have a couple of like chief translators. They spot check parts from the human. They make sure that you use the same style, the same translation memories, the same glossaries and stuff like that. And it's not sort of like 100 different translations. And then you merge everything because, like, you know, it's a big job and it has to be done like in 4 weeks or something like that. And the jobs are more shifting to that. Same in programming. I mean, these large language, but that doesn't mean that we don't need programmers anymore. No, on the contrary, you know, but programmers will happily use large language models to kind of like, you know, for this part of the thing, give me an idea and then I work with that. Yeah. And it doesn't mean that we need fewer or less, at least not at the moment. Okay. All right. So that's but going back to this architecture, so 6 encoder blocks, 6 decoder blocks. It turns out that they encode something that is a little bit like the sort of classical linguistic hierarchies, you know, similar to what you saw, the ghost faces and the piece of the nose and these edges and stuff like that, you know. But this is found by the machine, you know, and it's just determined by the architecture, by the training data, by the loss function, by the task you have. Okay, and it finds optimal representations for that, which are different from what we do. And often these guys are better. And this is, again, one of the reasons why neural networks can sometimes be surprisingly or amazingly good. Okay, so each of these encoder blocks, but each of these 6 encoder blocks in the transformer has 2 like sub-levels. Okay, and the first one is the self-attention, the second one is the feed-forward neural network. So in each encoder block, you know, when the sentence comes in, it first goes into the self-attention block, and the output of the self-attention then goes into the feed-forward neural network. And yeah, the cross-attention is between the top one. Oh yeah, no, and I should say, like, the decoder block has self-attention and then cross-attention, which is also sometimes called encoder-decoder attention, and also feed-forward neural network. So the encoder blocks and the decoder blocks are pretty much the same, apart from that extra middle layer where we do cross-attention, where we can peek into the top level of the encoder. Yeah? All right. And here's sort of like a picture about the self-attention. And let me explain it to that. So the sentence comes in. I make a copy of that sentence. It's actually not what happens, but kind of like for our understanding, it's easier. So this is our original sentence. The animal didn't cross the street because it was too tired. And you can see the subword encoding here. You see tired is not one word. Kind of like, you know, all the other ones are very frequent words. So the subword encoding has recognized them as words, like, you know, over the, I don't know, 50,000 iterations by just merging these characters, kind of like, but each word is now a single character just for the transformer. Okay. All right. The animal didn't cross the street because it was too tired. These are actually, that sentence is an example of a, what's it called? God. Can't remember the name. It's a famous professor in artificial intelligence from the 60s and 70s from Stanford, California. So consider a version of the sentence where I change one word. Okay, so the sentence at the moment reads, the animal didn't cross the street because it was too tired. Now I read you the sentence again, I change one word. The animal didn't cross the street because it was too wide. What does the it? Wide, yeah? So the animal didn't cross the street because it was too tired. What does the it refer? Yeah. And what does the it refer if the sentence is the animal didn't cross the street because it was too wide? So in the second one, the it refers to street, and then the first one, it refers to the animal. Yeah, do people see that? Yeah. And these are called, oh, what are they called? Kind of like, sorry? Yeah, it's co-reference, but these sentences are, so the original versions of these sentences were, the council refused to give a permit to the women because, for demonstration, because they feared violence. The council refused to give a permit to the women because they advocated violence or something. They're ambiguous. Yeah. I mean, it's kind of, so these are, oh my God, it'll come back anyways. And these sentences were, like, I don't know, 50 years ago, they were used to show that even ordinary natural language processing, kind of like NLP, computational linguistics, is AI complete. Because to get the most likely resolutions of these pronouns with these one change of words, you need so much world knowledge. You need that wide is a property of streets, not so much a property of animals, but tiredness is not a property of streets, but more likely of animals and stuff like that, you know, and that, yeah, you know, the council is more likely to fear violence. And, you know, this is a sentence from the 60s. Oh my God, Vinograd sentences, Terry Vinograd. So one of the kind of like, you know, big fellas in artificial intelligence. And they were used at the time to show that even ordinary natural language processing, like translation or anything, is AI complete. So you really need to solve all of AI in order to be able to do stuff like that, semantics and meaning and, like, you know, I don't know, cultural background and okay. And so now what happens? So you have that sentence, okay? You take a copy of that sentence, and then for each of the words in the copy, let's say you start with it, you compare it with all the other words in the sentence. Okay, and comparing means you just take the embeddings, you multiply them, kind of like, you know, you do vector multiplication. If the result of that multiplication is higher, then it's more similar, more relevant to the current word. If the number is lower, it's less similar. Okay, you actually don't take the original embeddings, but you send these embeddings through different spaces. The query, I don't know, can't remember the terms anymore, but you project them into three different spaces, and then you use those embeddings. And then what you do is kind of like, depending on how similar the words that you get in this attention are to the current word, you sum over all of the words in the input sentence, each one according to how similar it is to the current word. And you take that sum and make that the new representation of that word. And then you move on to the next word and you do the same thing. So do you see what I mean by this hyper-contextualization? Like, you know, the meaning of words is kind of like, you know, the companies they keep. And this is happening here kind of like, you know, according to the local sentence, and you bake into the representation of each of the words the context of that local sentence. And you do that at each layer. And actually you have, in the normal transformer, you have 6 of these attention heads that do this in parallel. Okay, so it's, yeah, there's a lot of stuff, a lot of contextualization happening. Yeah? Does everybody get this again? Okay, so what I forgot is query, key, and value. That's the kind of like, it's explained in the paper in terms of like an old database metaphor, query, key, and value. And what you have is, you have linear transforms, you have like linear projection matrices that take each of the word embeddings originally projected into a query space, a key space, and a value space. And that's the fellas then that you use in the comparison. Yeah. And you do that separately for each attention head at each layer. So there's 6 attention heads at each layer and 6 of these layers. Okay. So that 6 times 6 is 36 times this attention stuff happens. And you can see over here. So for example, 2, 4, 6, actually 8 attention heads. You see these colors there at the top? That's the 8 attention heads in that layer. And then you have 6 of these layers. So it's actually 8 times 6. So 48 times, this is done all in parallel, okay? So at one layer, it's all done in parallel, but each layer is sequential, yeah? Because in order to compute the second layer, you have to have computed the first layer. In order to compute the third layer, you have to have computed the second layer and so on, yeah? So it's in the transformer, it's parallel on the level of the string, yeah, completely parallel. So it's parallel on the input and it's parallel on the output in training, completely parallel. So all of this happens in parallel. But for these 6 guys, for these 6, that's sequential. So the entire input string, kind of like, let's say 500 words, all the computation in here in parallel for each word at the same time. But then the second encoder level needs the output of the previous encoder level to compute in parallel again its representations, even more contextualized representations for the 500 words, and so on. Do you see that? Yeah, everything parallel here, everything parallel there, except once you are decoding, when the system is trained, this guy will produce autoregressively. He will go from left to right, step by step. But in training, completely parallel because of this teacher forcing stuff. Okay. All right, and that's the self-attention. Do you get the idea? Would you be able to sort of like talk about this in your own words and why we're doing this? So the reason why we're doing this is that the word representations initially are decontextualized. They're static word embeddings. Remember that the one for can, the modal auxiliary, and for can, the noun is in the same word embedding because the string is the same, kind of like, yeah? But now we're taking the can and the modal auxiliary in its sentence, and we bake into the meaning of that can its context. Yeah, because that word is influenced by its context. And that holds for every word in that context. And this is what we're doing here, in parallel, for each of the words, no matter how long the sentence is. Yeah. Yeah.
What does it multiply? I mean,
Yeah.
This part I
Okay, very good question. So let me go back to... So that was the attention, okay? The basic cross attention for RNNs and LSTMs. And you compare hidden representations. You compare the hidden representations of the input. So this is the hidden representation that the input has processed the first word. This is the hidden representation that the input has processed the first 2 words. This is the hidden representation that the input has processed 3 words, and this one is the final one that goes out. And normally this goes out to the decoder like that, and we have this bottleneck. Okay, right. That's the hidden representation of the decoder, that it has already generated the first word, and that it's supposed to do all of that stuff. Because we still have that connection here. You know, we have to tell the decoder what to do. The decoder is the same as the encoder. It's just not reading in words, but it's producing words. Do you remember? Yeah, like we had the thing where it could produce something and it can produce a word. Yeah, and it can as a thing where it reads some input. Okay, and now this cross attention here takes this hidden representation here, which encodes what the encoder has done, what is supposed to be translated, and thereby also contains information about what to do next, because that representation informs the next generation step, okay? And if I just had this link here, that link would be bottleneck, because there's a fixed representation of this fella here, and that is not going to change, even if we stand on our heads, you know? He's not going to change. But now what's happening, I take that representation, that hidden state, and I pipe him back. See that line here? It goes all the way back. And here at that stage, I compare him with every encoder hidden state. So that's this guy here. And I compare him with that one. That's this guy here. I compare him with that one. That's this guy here. And I compare it with that one. And I make the comparison mathematically in terms of a vector multiplication. Okay. I take this vector and I multiply him with there. Okay. And if you have 2 vectors, okay, and the 2 vectors, you get a big number in vector multiplication. In fact, it's just the sum of the products, and that's a number. It's a scalar. If you like, you get a big scalar. If the vectors are orthogonal, product is 0. The vector product is -1. So from the numbers you get here, you can see how relevant these hidden representations, these different hidden representations in the encoder are towards the next generation step. Okay? And the way it's done is in terms of these multiplications. Then you take these 4 numbers that you got from the multiplications, from the vectors, you turn them into probabilities. That's what the softmax does. This is another nonlinearity. It just takes an arbitrary sequence of numbers and turns that sequence into a sequence that is probabilities. I mean, technical probabilities. And if you sum all of them, you get 1. Okay. And then it takes each of the resulting probabilities. So you get a low probability if these 2 vectors are not very similar. You get a high probability if these vectors are similar. You get an even higher probability if these are very, very similar. Then this fella here is relevant to that task. Okay. So you take each one of these original encoder representations, you weigh it by its probability, and then you sum over these. Okay. Again, you take everything, okay, like no, but weight it by how different the different parts are now relevant to that step. Okay. So that's where the products come in. And now we go to self-attention. It's the same idea. It's just that we're comparing words with themselves, and not decoder states with encoder states, which we also do in transformer because we have the cross attention. We have the decoder encoder attention as well. But the self-attention is now here. So here's the self-attention. And here you see an example. Okay. So we take the sentence, we copy the sentence. Each word in every sentence is represented by a vector. Yeah. Initially the word embeddings. Okay. What I didn't explain here is that I then map them into query keys and values, which are just linear projections. So just forget about that at the moment. And then what I do is I take, for the self-attention, I take the vector for this one here, whatever it may be, and I compare that vector to all of these vectors. And I do this by taking the multiplication of that vector with this one here. And it's vector multiplication, okay? It's not matrix multiplication, it's vector multiplication, so I get a single number. It's just the sum of the individual products, you know, vectors here, those two, those two, those two, those two, and then I sum over all of them and I get a number. And if the vectors are very similar, I get a high number, they're orthogonal, 0, okay? So for each of these multiplications, I get a number, okay? I take those numbers, send them through a softmax, make them probabilities, then I weigh each of these vectors here by the probability, how important they are for that word, and then I sum over them. And I take that sum of all of these, like, you know, component-wise sums of these vectors, which is a new vector, and I reassign this as the new meaning of it, which is now contextualized to everything else that's in the sentence. And according to how important it is to the it. Yeah. And this, I don't know, there's nothing in the system that tells the system to do that. This happens because of error-based learning and backpropagation. It's just you set the architecture up like this, okay? And then you hope that backpropagation will in error-based learning will help the system to come up with useful information here. You know, which of the it tries to learn which of the words are more important over time. You know, and you have this kind of like, I don't know, 50 million sentence pairs, and you train over them. You always know it's supervised learning because you know what the right target sentence is in the translation. Initially, it will just do completely crazy stuff. Will output total gobbledygook. You know, it actually is gobbledygook. It's worse than that. But you can compute a loss. You can compute an error because you know what the output sentence should be. Okay, you backprop through all of these kind of like these 12 layers, 6 encoders, 6 decoders, the internals, the attention heads and stuff like that, all the matrices, kind of like, which is just nothing other than weights, just linear weights. Yeah. So the art here is kind of like, so what the engineers and the scientists do here is they try to come up with architectures that are highly parallelizable, that do useful stuff, hopefully, kind of like, you know. But they don't tell the transformer to kind of like, you know, what words are more important to another one or something like this. They set up an architecture that allows, they know that to translate, you have to contextualize words because they mean different things in different contexts. And they allow with that architecture for that to happen. Any more questions? Yeah. Yeah. So if you have only 20 sentences to train on, no, not going to work. But if you have a couple of 100,000, you're beginning to be in business. That's a super good question. Also, remember the word embeddings that we talked about, these static word embeddings that are not contextualized. If you have only 500,000 words of text, they're not so good. Kind of like, because ideally you want to have sort of like, I don't know, a couple of million, a couple of dozens of millions, a couple of hundred of millions, a couple of billions is even better. Because you see more evidence, kind of like, you know, if you have like only 500,000 and there's one word that you're really interested in, but it occurs only twice, only two contexts from which the fella can learn. Unlikely to be very good. Kind of like, you know, the high frequency words, yeah.
Patients are good, you know.
Yeah, absolutely.
Better you have that.
Yeah. Yeah. So, a super good question. So all of these systems are, and this is a technical term now, crap in, crap out. You know, you're talking engineers, you know, and for good reason, of course. Kind of, it's crap in, crap out. If you give them crap to learn, they will learn crap. They will just learn what you give them. You know. Yep. Yep. Mm-hmm. Yeah. Mm. Yeah. Yeah. Yeah, it's a very good question. So at the moment, I'm just trying to explain the original canonical transformer architecture, encoder, decoder, sequence to sequence model, because this thing was developed for machine translation. Kind of like, so it's technology that was originally really just developed for machine translation. And then people found out, wow, it's useful for all sorts of other stuff as well. Okay. And modern large language models usually only use the decoder because they only need to predict the next word given a context. Okay. And so most of the large language models, like, I don't know, ChatGPT, Gemini, Perplexity, like all the ones that you might be using, like Llama or the Chinese models like DeepSeek, etc. They use that part of the architecture without cross attention because there is no encoder, you know, but just like the left to right prediction with a masked self-attention that, you know, in the training data does not, for each token at every stage, it does not allow you for that token to look into the what is the future for that token at that stage. But there are also language models that are only based on encoders. So if some of you have heard about like BERT models, like BERT as in the what's it called, the Sesame Street, you know, like it's one of the puppets in the Sesame Street. And a BERT model only uses encoders, and it's a masked language model. So you take the input and you mask words in the input, and you let the model guess these words, and you know which words they are because you have them in the input. Self-supervised learning, you know. So these are contextualized in a different way, you know. And there's a whole kind of like, you know, so the BERT style models, they actually precede like the decoder models, and there are papers about BERTology, you know, because there's so many different approaches and stuff like that. And it's like, I mean, you think that engineering papers are like, you know, dry to read, and no, they're very, very funny sometimes, you know, like attention is all you need, like BERTology, and they're full of stuff like that. Like it's sometimes really nice, actually. Okay, and yeah, everybody got the idea of self-attention now, and that this hyper-contextualizes, that the same thing is happening in the decoder, where the self-attention is just limited to whatever you already generated, because that makes an impact on what you do next. Yeah. And you, for each thing that you dynamically, the next thing that you compute, kind of like you again look at the input in a new way. Yeah. So it's no fixed input representation, but you just do all of that dynamically. And in training, input and output are presented in one fell swoop. So at the same time, it's trained completely parallel. Once you have trained it, you know, for machine translation, you just give it an input that goes parallel to the encoder, but then the decoder will generate the translation one by one by one by one, sequentially, autoregressively. But in training, completely parallel. Yeah. And to make that parallel, you use that masked self-attention trick. And this trick that's called teacher forcing, where you give the model, even though it might have predicted crazy stuff at the input level, you give it the correct stuff. Okay, but that goes into details. All right, yeah, and this is the byte pair encoding, the subword encoding. I think I explained that. I think I'm just gonna skip over that. And now, actually, yeah, this was exactly your question, kind of like, you know, so what models are used? So ChatGPT uses a decoder-only model. And in this decoder-only model, I learned to predict the next word from data. It's a language model, okay? And here you can see that this is the first word, second word, up to the nth word in the input. And I've got my training data over here, so that's a sentence or text or something like this. And then I get the first word, I try to predict the second one over here. I get the second one, I try to predict the third one over there, and so on. And you can see the information here from masked self-attention for each one of them only goes to the previous one. So this fella here only has access to those guys. That fella here would only have access to those two guys, and so on. That's the masked self-attention. And so, because if we told it what the future is, it would just copy and say, hey, I'm lazy. I don't want to learn this stuff. You know, it's written there. So I just, you know, give you the result. Yeah? And the other one is a masked language model on the left. That's a BERT model. Okay, and yeah, and here's sort of like an example for decoder-only transformer architecture, ChatGPT style, Gemini style. Like pretty much everybody is using these guys. And what you have here is you have some input. The chicken walked. And then it starts generating across the road or something like that, you know, or it tries to learn from this. And it's just a language model. It's just really next word prediction. You take the next word, you put it into the context, and you predict the next word after that, put it into an extended context, predict the next word after that, etc. And yeah, you see kind of like the blocks here. These are decoder blocks. Each decoder block consists of masked self-attention followed by feed-forward neural network. You know, same kind of stuff that you've seen before. And you also see the token embeddings and the positional embeddings. Again, you have to give positional embeddings with these sine waves and cosine waves and stuff like that, because of the parallel training. If you didn't give this, the transformer, like, you know, John loves Mary and Mary loves John would be the same thing, because there's no order in the words. Yeah. Okay, and now we come to sort of like, you know, some kind of like a summary. So we talked about conditional probabilities, kind of like, you know, and language models. So language models predict next word. One of the things they do is predict next word given a context, okay? And large language models do exactly the same thing. Your prompt, when you interact with the large language models, how do you do that? You ask it to do something. Huh? It's a prompt. And that prompt is the context on the basis of which the large language model will generate the next words. That's the only thing, you know? And, you know, a couple of like, you know, I don't know, how do you say this? There's a couple of bells and whistles, and we'll come to them, yeah? But it's really like that. It's just a language model. It's an autocomplete system, like you have in your phone. When you start typing in your phone, the thing will make suggestions, kind of like what's the next word? It will say, yeah, you misspelled that word. It's just a language model. And a language model is just that. It's context, and in that context, it will generate likely continuations. So if you ask in the prompt, like, you know, dear ChatGPT, who built the Eiffel Tower? You know, that's a prompt with a context, and it has built an Eiffel Tower, and, you know, it will probably kind of like generate, like, you know, what's the name of the fella? Jacques Eiffel or something? I don't know, something like that. Good question. Yeah. So, so a language model, remember, you have a context and then you have the next word position. And the language model tries to compute a probability distribution over all words in the vocabulary at that position. So you've got your context, you know who built the Eiffel Tower, and then you have the next word of the answer is the probability distribution over all words given that context. Okay. And the language models, if you constrain the language model to just print out the most likely word for all of you, and for some language models you can do that, then they will behave completely deterministically. So if you prompt, on the same day and the model hasn't been updated, you will get exactly the same results. But what they do normally is they don't give you just the most likely word, but they use that probability distribution. Some words in that context are more likely, some are less likely, to sample from these words according to the likelihood probabilities. So like, let's say there's only 2 words that are possible in that context. If one has probability 0.8, the other one probability 0.2, on 10 interactions with that model, 8 times, roughly speaking, it will give you the one word, and 2 times out of the 10, it will give you the other one. But it does that for the 50,000 or 500,000 over your vocabulary. And that's why kind of like, it will react differently to you, unless you force it, and unless you, under the hood, you can toggle switches, and you can say, language model, I only want the super most likely one. And then it's completely deterministic. Because there are no miracles. It's really just matrix multiplications and nonlinearities. There's no non-determinism or anything like that. The only non-determinism is kind of like in the sampling from the probabilities. And that sampling you can change in many language models with something that's called a temperature. And depending on how you set the temperature, so if you set the temperature very low, it will stick to that probability distribution. If you change the temperature high, it will go more into low probability words and stuff like that, be more creative, more crazy and stuff. Yeah, and some of the models you can also nail. But the nailing is often also not so good, because so when you're a language model and you predict the first word, and let's say you have to predict 10 words, if your first choice is the most likely one, that can actually spoil the whole rest. Yeah, because that choice nails you, and actually something that is really needed afterwards is now a very low probability, because kind of like you made that choice. And that's why it's often better to just pick from the probability distribution. If something is likely, yeah, you're going to pick it more often. But you can still pick the really crazy stuff. It just doesn't happen very often. Yeah. Okay, but these things under the hood, like totally, utterly deterministic. There's no one. Do you remember that cartoon? There's no miracles happening at all. Yeah. Any more questions? Yeah. Mm-hmm. Mm-hmm. Yeah. So if you have a super simple language model, kind of like just count-based and on discrete words, and if you train it on baby language, like baby says like ba 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 da 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 or something, that's your training data. It's just this one sentence. If you then train that model and then you say, please generate in unigram mode, that model can already give you output that you never saw in training. It can give you ba da ba da ba da, for example, depending on how probable it is and how you let it sample. It can generate output that is kind of like unlikely given the input, and you've never seen. Okay, and you can call this creativity or you can call this hallucination. It's the same mechanism. Kind of like, it's if the model finds something that we never saw and are surprised about, but it's a new discovery, then we say, goodness gracious, the model was creative. It found something that we humans never saw, because it's kind of like distributed over the data and stuff like that. But if it comes up with rubbish, like if it hallucinates, it's the same creativity, but it's just wrong. Yeah. And in the old days, kind of like, so for example, so okay, so let me just go back to this one here. So fundamentally, a large language model is just a language model, and you steer the interaction with that language model, what you want from it, through the prompt. You tell the model what you want, and this could be long text. This could be 5 pages or something like that, You could give examples, no examples, 1 example, 5 examples of. You could tell it how to format the output and stuff like that, kind of like, but that's all part of the prompt. Okay? And then given that prompt and given, that this is a language model, that given a context that will start generating, it will just do that, nothing else. Okay? Now there are a few bells and whistles, okay? Because in addition to the prompt that you give, kind of like, the companies, they slot in some invisible prompts as well, information. So these invisible prompts are like, to the AI, I'm a good AI. I'm going to help this customer. I'm not going to swear at it, because remember, these models are trained on everything, kind of like, and it's the good, the bad, and the ugly. And some of the ugly is worse than ugly. Yeah. And so if you didn't have these hidden prompts, and if you provoked it, it would happily generate pornography all day. It would generate fascist text, misogynist. It would abuse you. It would kind of like, because it's seen that stuff, it doesn't do it on its own usually. And remember, like, where the stuff comes from is us, not the model. It just sees some of the stuff that we dump on the net, highly offensive and whatever. But and so some of that is guarded in the hidden parts of the prompt, that you should support the person you're interacting with. That can also become too strong, because some of the older models, they tried to support the people that they was interacting with so much that they started hallucinating, because they had no idea. Like the old models, they were trained until, I don't know, maybe the model was trained until 2 years ago, the data from 2 years ago, because it's so much data and stuff like this. And then if you asked it kind of like, so what happened to Prince Harry? And not Prince Harry, Prince Edward, isn't it? That was demoted, kind of like. And if that model only had data until 2 years ago, it might say, oh yeah, he was promoted to I don't know, chairing the Bank of England or something. Yeah, not like that, But the model, there's so much pressure in the hidden prompts and stuff like that for it to try to help, that it's a little bit like, this old joke in Irish. So there's this, it's a beautiful country and lots of tourists and stuff like that. And this rich American fella comes drives all over the country and gets lost in the Wicklow Mountains. And no idea.
Sorry.
You can't turn your back on them, huh? Start trouble immediately. So that's this joke. So he gets lost, in his big Cadillac and stuff like in the Wicklow Mountains, and can't find his way back to Dublin. And he asks the farmer there with sheep, and what's up? Dear sir, how do I make it back to Dublin? And the farmer comes over and scratches his beard and looks at him and says, sir, if I was you, I wouldn't start here. And the models are like that as well, kind of like, they try to help up to the point where they force themselves into hallucinating, just making up stuff somehow according to probabilities and things like this. Yeah. But then the more new models so they also try to with the more new models, they try to train them, and I don't know, and that was completely absent from older ones. New models will also have access to the internet, so you can use something like you can interface internet searches, kind of like, you do your query, the model behind the scenes doesn't use Google or something like that, finds documents that are relevant to your query, to what you want the model to do from the internet, which is kind of contains stuff that was uploaded on the internet like 20 seconds ago. And this is called RAG, Retrieval Augmented Generation. So it takes these documents from the internet, and then it answers your query and extends that prompt, that context, but you don't see it. But it's now acting in the context of a prompt that is, I don't know, several hundred pages long, actually, and contains a lot of relevant documents that are completely new, that weren't used in training of the model. But because it has that context, its output is conditioned by that context, because it's conditional probabilities, kind of like, yeah. Mm-hmm. Yeah.
They are diverse, but they are like streamlining, I think, out.
Yeah.
Right? What? I mean, do the companies make sure they have some
Yeah.
mechanisms to prevent the machine?
Yeah.
I mean,
yeah. There's a lot of there's a lot of work on trying to distinguish kind of like real human text from automatically generated text that is generated by language models, because the companies, but also researchers, want to know, if they scrape the web and they take in data, and they at least they want to know and make an informed decision. Do I also take the model output into the training data, or do I don't want to do that? And so there's a I don't know, there's a race on between the model's output and getting better and better and better, and the tools that automatically try to predict whether a certain text is human generated or machine generated. That's actually an old problem already. So for example, if you like before large language models, when the web became really important and you wanted your documents to be super visible on the web. If you want to sell something or you publish a paper like archive or something like that, you want it to be visible. And even the old Google search engines and pretty much every search engine, they had methods of trying to predict whether text was human generated or automatically generated, even like in the old days. And they would rank automatically generated text slightly lower than human in the search results. And so what this, you might have heard about like a science that is search query optimization or something like this. There's entire companies that do that for you, kind of like, they make your web pages more findable on the internet and stuff like that. So what people do is, even if they generate text automatically, like, I don't know, like Amazon, most of the text like for the products is automatically generated, even before large language models. You just use rules and templates and like old machine learning based NLP and stuff like that. There was lots of work on generation. They then randomly introduce, for example, typos, spelling mistakes, to make it appear to Google like a human wrote this, because the humans, we put the comma in the wrong place. Now, I do commas like this, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, comma, 1, 2, 3, 4, 7, 8, 9, 10, comma, which is wrong. I have no idea why, but it's wrong, But yeah, it's an old problem. And of course, the companies are really interested because they may not want to contaminate their training data, or they may say like, this is really cool training data, but we want to know, we want to make a conscious judgment whether to include that or not. Yeah, there's lots of work on that. But there's also people that predict that the internet is going to die because everything will be automatically generated at some stage. Yeah, I don't know. Yeah. 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 That takeaway, everybody got that? That at the end of the day, it's just a language model. And now we come to the bells and whistles. Because at the moment, ChatGPT, so a big model like ChatGPT, like Gemini, or the Chinese models, or the Russian models, or I don't know, the European models like Meta or Llama, or and other European models and stuff like that. The first part of training is just training as a language model. So just predict the next word. And, like usually pretty much all the data, like the bad, the good, and the ugly. Sometimes people also filter training data to try and get out the worst. And there's always a question about censorship, yeah. And then they have mechanisms for kind of like, even though they're trained on this, they have mechanisms for either allowing people to say, yeah, I want this unfiltered, or I want you to be cautious. I want to give this to my children. And yeah, you want to be able to, but you can do that before or after. Yeah. But so that first step of training is really just next word to prediction, and it's called pre-training. And that way, the language model learns about language, do you remember the word embeddings that we saw? There was grammar in there, there was culture in there was meaning in there, and stuff like that. We could do addition, subtraction, and things like this. And same here. So this pre-training, by just learning the next word. Yeah, and you can see that these models learn stuff that that corresponds to linguistics. So you have like, if you remember linguistics, like there are so-called island constraints where you have pronouns in embedded clauses that they can only refer to this, but cannot go outside and stuff like that. And you can say that the sort of like probabilities or the confidence of the predictions relates to these island constraints. Kind of like, island constraints are highly theoretical constructs that people like originally, I think, goes back to like Chomsky and stuff like that. And these guys learn similar things just from data, nobody telling them. It's just that their confidences go down if you force them to predict kind of like something ungrammatical and stuff like that. Probabilities go down, and you can see there's some quite interesting interactions with them. So in this pre-training phase, they learn about like language structure, words, domains, meaning. It's all very woolly, of course, and modeled together. But that's what the pre-training does. But then, as I said, these models would be raw. They would be raw in the sense that they would not be good conversational partners, because a lot of the data on the web is not conversations, it's just text. And you don't have the he said, she said, he said, she said that you want, you want to interact with the model over like maybe a couple of hours, refine kind of like and they're not very good at that if they've just been trained on next word prediction. So then in a second part of training, which is often called fine tuning, or there's a couple of other words that come on the slides, you first help the models to become good conversation partners. Okay. And you also do a further step of aligning the models with human values. And of course, this is not absolute. That depends very much on the culture. If you're in China, the human values say Tiananmen Square did not happen. And you can also see how these things can be abused for propaganda and stuff like that. In other cultures, other things. You mean your children not to see this or stuff like that. But that's sort of like alignment with human values, and that is done on the pre-trained model that has just learned next word prediction. So it gets lots of questions, and you get the answers of the model, and then human people originally, actually tens of thousands of people or hundreds of thousands of people, very often in Africa and other parts of the world, rated the output of the models. They say that's a good answer, a bad answer, or they get like 3 outputs from the model and they say that's the best, this is worst, that's worst. Not giving an absolute judgment, but just like, rating them or something like this. And this judgment information, this rating information is then used to further refine the models in something that's called reinforcement learning based on human feedback. It's called RLHF, reinforcement learning on human feedback. And reinforcement learning is another type of machine learning. So we had supervised learning, we had self-supervised learning. There's also unsupervised, which we didn't look into this course. We would do that if we did sort of like introductory course in machine learning. But not in this one here. And then there's also reinforcement learning. And reinforcement learning is usually where you have like a long interaction and you get your feedback only at the end of the interaction. It's a bit like walking through a maze. So you have to try lots of turn, and only at the end, if you're stuck, you get a bad feedback because you're stuck. You didn't get, or if you found the exit of the maze, at the end of all of these choices, the long path, yeah, I'm outside, I made it. And this human feedback on interactions with the system are like that, because it's only at the end of the conversation, the human says, yes, good, oh, that was pretty awful, And then this is then used, that information is then used to refine these large language models. In the post-training, or what was this called again, terminologies with the pre-training, with the fine-tuning, the aligning with human values and stuff like that. So there's a mix of things that happen there. And usually for the large language models, you can't do this with just humans. Even if you have like 10,000 raters, or 100,000 raters, you have so many languages and stuff like that. So what they do is kind of like, instead, is from the human data, from the human evaluations of how the raw language model that just do next word prediction, how that works, they train a smaller model, a little classifier, kind of like, that is then used as a classifier to automatically rate large language model output. Kind of like, and then you can do this on scale. You can do this for like, I don't know, 100 languages. And this works day and night in parallel and stuff like that. If you just did it by humans, it's not scalable. You can't do it. It's too much. Yeah. Okay, so let's just go there. But that's the initial takeaway. Initial takeaways is just a language model. Your prompt gives the context. There's some hidden stuff there as well, which you don't see. They're usually kind of like precautions and things like that. And then the model will generate. Like just, outputting, next words. And this is the same in machine translation. Machine translation is like a conditional probability. So you give the source sentence to be translated as the blue bit here. That's the conditional probability. Remember, in these probabilities, like the bar, the right thing on the bar is the conditional probability, and then it will generate, depending on what it has learned, where it has been trained with bytext, it will produce some output that is a likely output given that conditional probability, but it's an output in another language. That's machine translation, and the same with the ChatGPT, like, and so here's an awful joke, philosopher's joke, asking ChatGPT, tell me a joke about Immanuel Kant. I can't, like that's actually, I got this joke from Ricardo. who's going to join us, I think tomorrow in the meeting. Yeah, or maybe Christoph. I can't remember now. But anyway, it's an awful joke. Terrible. Actually, these models are often not very good at jokes. You know, that's quite it's so cringy sometimes. You know. But you see, it's the same thing. It's the same as machine translation. It's the same. It's just kind of like your prompt is just, you know, providing some conditioning context, and then it's generating in that context. It's generating stuff that it finds likely from what it has learned. Yeah, do you call that intelligent? Or you remember the big questions that we had? Are these systems conscious and stuff like that? You know, and now put these things together. But yeah, I mean, in some sense, they're just autocomplete systems. But then there's all the bells and whistles because, like, as I said, like, you know, a system is not just trained on next word prediction, but there's this other stuff. Because if you just train on next word predictions, these systems aren't very good as at conversations. And the reason for that is that most of the data, and this is kind of like, this is really large amounts of data. Like we at our place could not handle all of this. You know, and that's the DFKI, the German Research Center for Artificial Intelligence. We have really strong computing and stuff like that, but this is just too big. But a lot of that data is just not conversations, it's really just text, so it's not very good at conversations. So that's why training of these really commercial and also research large language models comes in two phases. The first one is called pre-training, and it's just the next word prediction. It's self-supervised training because the supervision signal is in the training data, because you always have the next word. Yeah, you know what it is in the text. So you don't need annotations or anything like this. And from that, it learns about language, the meaning, domains, topics, and what have you. And then you the fine-tuning, and sometimes also called, that's the word that I forgot, instruction tuning large language models. And this is to make it, on the one hand, easily interactable. You can instruct it what to do, and that it reacts well to that, etc. It responds with what you expect and things like this. That it can engage in lengthy conversations, lots of turn taking, like he said, she said, and so on. Because you can actually converse with them over days, and they will still remember what you said a couple of hours ago and stuff like. If you keep the session alive. Okay, or you can also tell the model to save your old sessions and to pick that up and stuff like that, because often they can do, I don't know, they can remember 50 pages, 100 pages or something like that. Some models even theoretically infinitely large context. And then the other thing is kind of like you want these models to be civil, non-abusive, you want them to be supportive and stuff like that. And that second part is usually done with reinforcement learning with human feedback, as I explained, kind of like, you know, where you give lots of examples and you let initially humans rate this. And then from those ratings, you train, also using neural networks, you train little classifier models, little classification models, and then you let these automatic models, the rating models, loose on, and you let ChatGPT and all these systems automatically produce output, and you just rate it automatically, and you feed that then back into the model with reinforcement learning so that the models become better. And this is just kind of like the little models are just to scale the approach, because there's not enough humans on the planet to do this in all the languages. So how do we interact with the large language models? How do we get at what we want to do? We want it to do, yeah, we prompt it, you know? And this is just kind of like reinforcing the same thing, kind of like, you know, it's just providing a context. A prompt is a context, is a conditioning bit in a conditioning probability, and the LLM then generates in that context. But where at that stage, it's no longer just next word prediction, but it's next word prediction refined by this human alignment, by this ability to have changed the probabilities in such a way that it can happily chat. You know, you say something, it says something, you say, please refine this, or give me a picture, give me a little, or explain this to me more easily, or, you know. Okay, so it's really like, you know, at the end of the day, it's an autocomplete system, a sophisticated autocomplete system, but nothing else. Then with these prompts, because the prompts are so important, the prompts tell the model what you want. And that's why it's important to know about how to do good prompts. And this is the subject of prompt engineering. So sometimes if you want the system to do something complex that is not sort of like run of the mill, it's good to give examples. Okay, you could either give no example, that's called zero shot in your prompt. You could one example, that's one shot. A couple of examples, 2, 3, 4, something like this. That would be few shot. Or you could also ask the model to explain how it came to this answer. And this is often called chain of thought reasoning. And by the way, these things are also usually trained in the instruction tuning phase. So the model is presented with like one shot, zero shot, exactly, and human feedback, and the model is using that human feedback to refine itself to be better at one shot, zero shot, blah, 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 and chain of thought and things like this. And here's just a few examples. So I actually asked Gemini to itself give some examples of zero shot, one shot, few shot. So here it's kind of like what it said. In a zero shot prompt, you give the model the instruction and the input without any examples. That's why it's called zero shot. Don't give it any examples. You rely entirely on the model's pre-existing knowledge to complete the task. So here's the prompt, like, determine the sentiment of the following movie review as either positive or negative. And then you give the movie review. The acting was stiff and the plot made absolutely no sense. Yeah. And then you hit the return key, and then the model will probably tell you that, probably this movie was pretty bad. Kind of like, or like movie reviews are easy for these systems. A one-shot prompt version of this would be like that, but with an example. And here's the one-shot prompt. Again, the prompt is determine the sentiment of the following movie review as either positive or negative. And now you give the example. You give the review. This film was a breathtaking masterpiece from start to finish. And then you say sentiment positive. That's the example. Yeah. One example. And then you say your turn review. That's the new review. So your turn tells the system now here's the new stuff that's coming that I want you to review. The acting was stiff and the plot made absolutely no sense. Sentiment, colon, and then the system will generate. So the context of its generation will now include an example of what you want it to do. And you can also use these examples to tell the system how you want the system to format its output. Kind of like, so here's a few shot prompt, only getting smaller and smaller and smaller. Apologize about that. I can't see what's on this prompt here. Yeah, so it's determine the sentiment of the following movie review is either positive or negative. And then you give 3 examples. Example 1, review. This film was a breathtaking masterpiece from start to finish. Sentiment positive. Example 2, review. It was an average movie. Nothing spectacular, but an okay watch. Sentiment positive. Third example, review. I walked out halfway through it. It was that dull. Sentiment negative. And then your turn. That's the thing that you want the model actually to tell you the sentiment about. The acting was stiff and the plot made absolutely no sense. Yeah, it's really easy. Like, the zero shot, one shot, two shot, and you can show that for many tasks. The more examples you give it, the better it gets. Because you nail the context more, kind of like, and especially if you could ask the model, like, any syntacticians here in the room. Linguistic syntacticians, you could give it a sentence and you could say kind of like, give me a plausible phrase structure tree for this, and it would do it, and it might do it better if you give it a couple of examples. Okay, then, yeah, here's a summary comparison. So zero shot is no example, one shot is one example, few shot is just a couple of examples. You don't want to give too many examples as well, because it gets very tiresome. And the benefits are like zero shot is just quick and dirty. And it just uses the baseline knowledge that the model has anyways, and one shot may help you to even communicate the output format, input-output format that you want the model to produce its answer, and few shot might give you just better results, and accuracy on nuanced tasks. Okay. Okay, here, the next example is where you ask the system to do some chain of thought reasoning. So you ask the system to do something and to explain how it came to the conclusion, and this has to be really taken with a pinch of salt, because like how does the system generate this? What's the basic mechanism? Yeah, language model. Okay, just context, kind of like, and its explanation of what it thinks it did may not be what it actually did, but it might just be very likely in that context. Yeah. So, but at the same time, people have shown that if you ask the system to explain itself, it can sometimes produce better results. It can even, like in a chain of thought, it could even kind of like, in that conditional prediction, it could even overthrow some stuff that it has done earlier and say, hang on, methinks that, maybe, and I think this might be an example of it here. So So here's the prompt. It's a long prompt. And because we have some philosophers involved, it's a philosophy example. So the prompt is from here to there, kind of. And this is all explanation. And here then you ask for reasoning and the conclusion, okay? And the problem here is you're an expert logician. Analyze the following statements and determine which person must be lying. Provide a step-by-step explanation of your reasoning before stating the final conclusion. And here's the example case, kind of like, so you give actually, is this 0 shot, 1 shot, 2 shot? What is this? It's 1 shot, yeah, very good. Yeah. So it's 1 shot with explanation. So example case, Alice says Bob is lying. Bob says Alice is telling the truth. And your human reasoning that you provide for this is that if Alice is telling the truth, then Bob must be lying. If Bob is lying, then Alice must be lying. Contradiction, therefore Alice must be lying, which means that Bob is telling the truth. Conclusion, Alice is lying. So this is supposed to be done by the human. Do you agree with this or not? The logicians are shaking their heads, and they're right. You know, it's this is actually the liar paradox. You have no idea who is true. So here, it's actually interesting. So Gemini generated something that a human would do as an example. And, you know, I guess humans make this mistake as well in some sense, yeah? But anyway, so if you run this and, hello, do we need to go or? We stop? Yeah. Okay. Yeah. But you know, so maybe just we do this quickly, kind of like, you know. So here it kind of like then. So this is then the output of the model. If you ran that prompt, you know, it says David is telling the truth, Charlie is lying. Step-by-step reasoning, and then it goes into the assumptions and contradictions, and itself in the explanation finds that this is an example of the liar paradox. And you can't actually say this, kind of like, you know, so yeah. But it's not guaranteed that a self-explanation in a context actually corresponds to how the model under the hood reasoned. It could be like this, but it could also just be like a plausible generation in that long prompt context. Yeah, and these two things could be similar, could be different. Okay, then prompt tuning, you can also tune the prompts automatically, but I think that's too advanced. And then the final thing that I want to do is just this retrieval augmented generation where you can give access to documents to the model in the prompt effectively. So for example, if you wanted to do something about Kant and you wanted to use the whole model, you could take all Kant's works, like, you know, I think 1.5 million words he wrote or something like this. Or if you want to do something with Shakespeare, you could plonk in all Shakespeare. And of course, the model has read Kant and Shakespeare and stuff like this. But if you plonk this in, kind of like in the prompt, then the context is even stronger than what it has read, you know, read in inverted commas. And you can also add context that is completely new, because the model was trained, they finished training the model maybe a month ago. So that model doesn't know anything about what happened to Prince Andrew, kind of like, you know, but, you know, you can interface it with a search engine where the model then uses the search engine as a tool. Kind of like the model itself then, you know, has software components that interface it with the search engine. It says, give me the news information about Prince Andrew in the prompt, and then it will more likely be answering the question correctly, even though it has not seen the recent developments about Prince Andrew, like in, you know, and this is retrieval augmented generation, kind of like, you know. And yeah, I guess we have to kind of like, otherwise we're going to kick off. So we stop here. Thank you very much for listening and for being such a nice audience and for all the questions and everything. And hope you enjoyed it.
But the next ones also have to be there. Something.
So much of a good thing.
Too much of good things there. Yeah. Now, we also know actually now three. Tomorrow morning, 11:30. 11:30. No, not Helena. Stimulus.